Hello students. Today we are going to start this discussion by talking about conductors, those particular materials able to conduct electricity. We start by recalling that all matter is made up of tiny particles called atoms, consisting of a positively charged nucleus with negatively charged electrons orbiting around it. Normally, atoms have equal numbers of positive and negative charges, which makes them neutral, meaning that their net charge is zero. But some atoms may easily lose an electron, leaving an atom with an unbalanced number of positive charges, and the atom is now called a positive ion. This is so in metals, where atoms are found to have one or more electrons not tightly held to the nucleus. The structure of metals can thus be seen as being composed of vast arrays of positively charged ions vibrating about fixed points, as shown in this diagram. Okay, so these gray circles with positive sign are showing the positive ions vibrating about a fixed position. Then, obviously, there are the negatively charged free electrons, which here are shown by the green spots, wandering randomly between them. Of course, overall, the metal is neutral. We are not saying that it is positively charged, but we are saying, I repeat, that its structure consists of these positive ions, which have a fixed position and they are vibrating due to thermal energy about that position, and the loosely bound electrons are free to wander randomly and chaotically around the metal. Now, if we had to apply an electric field across a metal sample, in other words, we apply a potential difference or voltage across the metal, such as by connecting a battery across a copper wire, then we find that the free electrons are all accelerated towards the positive terminal of the voltage source. Okay, so as you can see now, these green spots signifying the electrons have all gained a velocity towards the positive terminal of the battery. We say that a drift velocity, v, is superimposed on the random motion of the electrons. An electric current through a metallic conductor, in fact, consists of electrons drifting from the negative terminal through a closed circuit towards the positive terminal of the electrical supply. So here we are showing the direction of the electron flow from the negative terminal towards the positive terminal of the power supply. Now, to help you understand the concept of PD, short for potential difference or voltage, okay, these mean the same, you can simply imagine a water stream that flows from a high point to a lower point. As you know, water only flows if there is a gravitational potential difference, meaning a difference in height between 2 points. Now, the flow of water is analogous to the drifting free electrons, which likewise, therefore, need an electric, obviously not a gravitational PD, an electric PD to form an electric current, and this is provided by a battery. Now, as electrons drift inside the conductor, okay, so as they travel through the metal from one end to the other, it is very likely that they undergo collisions with the large vibrating positive ions. You must also keep in mind the size. Electrons are much, much smaller than the vibrating positive ions. Thus, the probability of collision is very high. And we say that electrons are thus resisted in their motion. So every electrical conductor is said to have a resistance, and this is measured in ohms. So the resistance of a metal is due to these collisions between the drifting electrons and the vibrating positive ions, which we measure in ohms. The term drift velocity is defined as the average velocity at which free electrons travel through a conductor when under the influence of an electric field. Okay, so we have the definition here for drift velocity. Now, if we take a look again at the figure, you may have noticed that the direction of electron flow is, as we said, from the negative battery terminal towards the positive. Okay, so from here to here. This may look like an anomaly, since, as you know, current is conventionally taken to flow the other way around. In other words, the current signified by I is taken to flow the other way around, that is, from the positive terminal of the battery towards the negative. So as indicated by the red arrow, which is in opposite to the green arrow. Now, this might confuse you, but the reason behind this anomaly is that when current electricity was first discovered, some scientists believed that electric current in metallic conductors consisted of a flow of positive charges, not negative, which drifted away from the positive towards the negative terminal of the supply. When it was eventually discovered that it was all about the free electrons that drifted in the opposite direction, some countries, including England and Malta, maintained the old convention, and with us call this the conventional current I, and we are going to stick to this convention. That is, current I is always taken to flow from plus to minus, even though we know that the electrons actually flow the other way around. Okay, don't let that to confuse you. Now, let us derive a formula that expresses the electric current I, relating it to the free charge carriers. Let us consider a section of a wire of length L and cross-sectional area A. Let capital N represent the total number of free electrons in this wire sample. So, if we had to define a small n, which means the number of free electrons per unit volume per meter cubed, then we have to divide the total number of free electrons by the volume of the metal sample, and the volume is the cross-sectional area times the length. So if we change the subject to capital N, we get capital N is equal to small n times AL. Now, the drift velocity of electrons, which is the average velocity by which the free electrons traverse this section of the wire, is given by distance on time. So it's the length of the metal sample divided by the time taken for the free electrons to traverse this section of the wire. So we have V equals L on T, or L equals Vt. So we can substitute this L here with Vt, and we end up with capital N is equal to small n A times Vt. If we had to calculate the total charge, capital Q, in this metal sample, then we have to multiply the electron charge E by the total number of free electrons. So the total amount of free charge is simply NE. But we have an expression for capital N, so we substitute by nAVT, and we end up with nAVTE. So the total free charge Q is nAVTE. Or if we reorganize the equation, we get Q on T is equal to nAVE. Now, the electric current, capital I, is defined as the rate of flow of charge. In other words, if we had to write this definition mathematically, we are saying that I is equal to dq by dt. I am hereby using the differential notation. Or simply, if we deal with uniform or constant current, it simply becomes Q on T. So I, the constant current, is Q on T. So you may easily see that in this equation that we have derived, the quantity Q on T is equal to the electric current I. So the final equation is I is equal to nAVE. Okay, so for the sake of the exam, you may be asked to derive this equation. Now, some typical values, not to learn them by heart, but to let you get an idea of what we are talking about. First of all, the equation that we have just derived shows that the amount of current flow through a material depends on the number of free electrons per unit volume of that material. For good conductors, for example, copper, we find that N is of the order of 10 to the power of 28 per meter cubed. Obviously, perfect insulators have no free electrons such that small n ideally is equal to 0. In insulators, no electrons are free to move unless under extreme conditions such as very high temperatures or very high PDs that may break down molecular bonds. A typical example of this is when lightning strikes, even though air is an insulator. But those, as we said, are extreme conditions. Now, there are some materials whose conductivity lie in between that of a conductor and an insulator, and we call these semiconductors, having a value of N of the order of 10 to the 16 per meter cubed. Examples of these materials are germanium and silicon. Semiconductors shall be dealt with as a separate topic, so we are not going to discuss them yet. Now, drift speeds are surprisingly rather small. So we are saying 10 to the power of minus 5 to 10 to the minus 4 meter per second. So this means that electrons travel rather slowly in circuits. However, do not be misled, because free electrons are found at every point along a circuit, and hence, applying a PD, they all start to drift immediately upon switching on, thus producing immediate current at every part of the circuit. So that is why a bulb, for instance, lights up the very moment you turn on the switch. So don't think that by having these slow values or small values of drift speeds, we get a delay when we switch on current. And the reason is the one I've just mentioned. So, what does it actually mean to say a current of 1 amp? The official definition states that the ampere is defined in terms of the fixed numerical value of the elementary charge E when expressed in coulombs, where the unit of coulomb is equal to ampere second. Let's reword it in simpler words. So we are saying that a current of 1 amp means that 1 coulomb of charge is drifting past a fixed point in the circuit per second. And what do we mean by 1 coulomb of charge? So if 1 electron has this amount of charge, 1.6 times 10 to the minus 19 coulombs, this is the constant which we refer to as E, then 1 coulomb of charge will have how many electrons? So it is simply 1 division by the charge E, which gives us 6.25 times 10 to the power of 18 electrons. So we are saying that 1 amp means practically 6.25 times 10 to the power of 18 electrons per second. If we had to consider a graph of charge against time, for instance, the one I'm showing, so with the charge on the y-axis against the time on the x-axis, then you must note that the gradient dq by dt is equivalent to the current I. So the gradient gives the instantaneous current in the circuit. On the other hand, in a graph of current against time, I am hereby showing a simple case where the current is constant or uniform. Then the area enclosed, hereby shaded by yellow, is equivalent to the total flow of charge, capital Q, in time t. At the end of this session, I am providing a simple problem for you to try at home. It is intended to get you started with the equation I equals nAve VE, but please pay attention for the units. The final answers I'm showing also here.